Hi, thank you for joining us today. In this video, I'm going to show you some tricks and tips on how I created this flamethrower scene. Before we begin, it's important to note that this video assumes you have some basic knowledge of Phoenix and particle simulations. It's not a step-by-step tutorial, but rather a demonstration of techniques and concepts. Those are the topics I'm going to cover in this video. And I used specific software to create the scene. If you want to utilize the grid-based motion blur feature, make sure you have Phoenix 5.10 or a newer version. Now, let's dive right in and get started. First, let's talk about the modeling process. When working with fluid simulations, it's crucial to ensure that the model is watertight. This means there should be no open faces or errors when applying an STL check modifier. If there are any issues, Phoenix might encounter difficulties when voxelizing the model during the simulation process. Let's take a closer look at the model. As you can see, the wood planks are not overlapping, but positioned as if they were realistically nailed together. It's important to note that each component of the tower is a separate geometry. This allows for easy manipulation of its dynamics within the particle system. Furthermore, ensuring that the z-axis in local space aligns with the longest direction of each wood plank enabled me to utilize the volume break operator in thinkingParticles. This operator helped me fracture the planks into longer fragments, which we will discuss in more detail later on. Once the model is finished, we can proceed to import it into the particle system. In this case, I'm using thinkingParticles. However, I'll do my best to explain the concept of my setup so that you can apply it using other tools like particle flow or TieFlow. Here is a preview of the particle effects in action. As you can see, the flamethrower ignites the watchtower, leading to a dramatic explosion. The tower then crumbles, and debris is scattered in all directions. This diagram illustrates the different particle groups within the scene, each color-coded for easy identification. We start with the flamethrower particle group represented in orange. The wood group, shown in green, is subsequently ignited by the flamethrower. Once ignited, the wood fragments begin to burn. After a few seconds, there is an explosive reaction depicted in blue, generating explosion particles represented in white simultaneously. Now, let's examine the dynamic sets in thinkingParticles and explore how the nodes are interconnected. While thinkingParticles allows for intricate setups like hinges or constraints between wood planks, for this demonstration, I have used a simpler setup that suffices. However, feel free to expand and enhance the scene in the future according to your preferences. Let's start with the flamethrower particles. In the node operator, a box is used as both the source position for the flamethrower and as a control to determine the direction of the particles. As you can see, I can rotate the box to control which direction the flamethrower to torch, simply by rotating the box. Moving on to the burning tower, I import all the tower geometries into thinkingParticles using object-to-particle operators. In this case, I utilize 4 object-to-particle operators for the tower, metal plates, oil barrel, and ladder, respectively. With the tower now inside thinkingParticles, we can activate the pre-fragmented wood planks and convert them into the burning wood fragment group. To achieve this, we utilize the psearch node as the condition. In the node operator, I have animated a dummy object that moves from the bottom to the top of the tower. By setting the proximity distance, the wood particles transition from an unburned state to an active burning state. As you can see, when the dummy object approaches the green wood, it changes from green to red. By moving the dummy from the bottom to the top of the watchtower, we can emulate the spread of the fire across the wood planks. Here, I am using an Omni light to trigger the explosion. Even though this seems strange at first sight, it's a standard technique, and the light is intentionally positioned near the oil barrel. Let me adjust the position of the light to a lower position and cache the particle again. As a result, the explosion will now occur in the lower section of the tower. Here is the dynamic set we use to activate the explosion. It incorporates an Omni light within the light condition node, and the time interval node allows us to trigger the activation at a specific time. The Omni light also played a role in determining the direction of the explosion. By assigning a negative speed value in the velocity node and inputting the Omni light position into it, the light now serves as the central point of the blast. One of the advantages of using light as a condition is the ability to control its impact on surrounding particles by adjusting the falloff of the light. Let me select the Omni light and increase its falloff. After Cache TP's particles again, you'll notice that more wood fragments have been activated for the explosion. Now that we've explained how we activate the particles and how they transition from one group to another, let's discuss the fragmentation process. It was achieved using the volume break node. To create realistic wood fragments, we adjusted the X, Y, and Z scales in the volume break operator. As you can see, on the right side, we have achieved more realistic and convincing wood fractures, while on the left side, the fractures appear uniformly Voronoi-like. Now that we have the wood shattering into pieces, we still need to create additional particles for the explosion. These particles will be used to feed into Phoenix as fuel and a high-temperature source. The white particles in the screenshot are the ones we're going to create. When creating particles for the explosion, I want to avoid a uniform, homogeneous emission of particles. I want some pattern, like the one on the right. Here we have an example of homogeneous particle emission. If we were to use these particles as the source for the explosion, it would lack definition and appear more like a large smeared fireball. Therefore, instead of homogeneous particle emission, I aim to create some clustering with these particles. A similar setup can be found in the artillery explosion tutorial available on the official documentation page. In the example of the artillery explosion, you can observe that the particles have formed distinct clusters. This clustering effect enhances the overall visual impact of the explosion. Allow me to explain the process of creating the explosion particles. To begin, I utilize thinkingParticles to generate a geometry, which in this case is a sphere. Next, I generate several seed particles on the surface of the sphere. These particles are aligned to the normal direction of the sphere. Using the positions of the seed particles as a reference, I generate the explosion particles with slight position variations. These explosion particles inherit the direction from the seed particles, which plays a crucial role in creating a more pronounced and distinct explosion. Those are the actual TP nodes I used. To begin, I create a sphere, but you can use any other geometry as well. Next, I used the sphere as a source of seed particles through the matter waves operator. It allows me to utilize the sphere's normals as the direction for the seed particles. Using the seed particle's velocity and position as a base, I generate additional particles for the explosion with some positional variation. Alright, though, there are other minor settings such as gravity and shape collision. They are very regular and nothing special. Let's move on to the next stage. With the completion of the rigid body simulation, destruction effects, and particle generation, we now have the necessary elements to integrate them into a fluid simulation using Phoenix. There are 3 Phoenix sources in the scene, one for the flamethrower, one for the burning wood, and one for the explosion. Note that both the flamethrower and explosion use particles as emitter nodes, while the burning wood uses the object as an emitter, so that the fire opacity can be modulated through the same object. We will discuss some key settings for each of them. Let's start with the simple task, the flamethrower. To do this, we will create a Phoenix source helper and select the particle group for the flamethrower. To add thinkingParticles particles as an emitter in Phoenix, follow these steps. With the flamethrower source selected in Phoenix, locate the Add button. Click on the Add button and choose the thinkingParticles node in the scene. Phoenix will generate a list of thinkingParticles particles for you to select from. From the list, choose the particles that correspond to the flamethrower effect. By doing so, you are instructing Phoenix to use the selected thinkingParticles particles as the emitter for the flamethrower simulation. For a realistic pyro effect, we don't emit smoke directly from the source. If thick smoke and fire are emitted at the same time, they overlap too much, which is not very convincing. Instead, we set the source to emit high temperatures and fuel, and then allow the fuel burning to produce smoke. In the fuel rollout of the simulator, we can adjust the smoke threshold and smoke amount to achieve a good balance of fire and smoke in the shot. Okay, before we dive into the dynamics, let's take a look at the volumetric render settings. Here's an image rendered with the default values. It's not too bad, and could be suitable if the director wants thick smoke and is not concerned with losing details in the fire shading. However, if you want to bring back detail in the hot region, you have to adjust the gradient and curve. After fine-tuning the volumetric settings, we have rendered a new image that showcases the updated visual result. In this image, the color gradient represents different temperature levels, with the core of the fire displaying a subtle blue tint. The curve has been carefully adjusted to maintain detail in the lower temperature regions while avoiding overexposure in the high temperature areas. Moving forward, we will continue using these adjusted volumetric settings throughout the demonstration to ensure a visually appealing and realistic representation of the fire simulation. Here, I have created a simple animated cylinder as an emitter, as a simplified version of the tower. So here we have results of emitting fluid with and without adding a mask in the outgoing velocity of the source. To be honest, the one without a mask looks more convincing, since masking the emission reduces the total output of the fluid and makes it appear weaker. However, we can fix this by switching to a different conservation method later. Just keep in mind that using a mask in a source can improve realism. To make the fire more interesting, we animate the X, Y, and Z offsets of the noise map as a mask, so the fire won't emit from the same spot all the time. In the dynamic settings of the simulator, the default conservation method is set to PCG. However, in this case, it seems to produce better results when I switch it to direct smooth. In addition, I also added a phoenix turbulence and a plane force in the scene to introduce some randomness, and the fire at the base looks too sharp. To smooth it, we can add a V-ray distance texture to modulate the fire's opacity and reduce the issue. Now our fire is really taking shape, isn't it? Here are the settings for fire opacity modulation. We insert a V-ray distance text in the texture slot. Add the cylinder geometry in the V-ray distance text objects list. You might ask, how about particles? Can we add particles in the objects list in the V-ray distance map? No problem. In thinkingParticles, there is a feature called Groups as Objects in the Master Dynamics rollout. By enabling this option, you can turn particle groups into regular objects. Therefore, you can add those particle groups to the V-ray distance text objects list. By the way, the Groups as Objects option also allows us to add the particles as objects in the burning wood source, which is a different approach by adding flamethrower particles in the emitter node. Let's continue with the animated cylinder. To further improve the realism of the fire, we can experiment with the motion blur option in the simulator's rendering rollout. Switch the motion blur mode from ray traced to grid-based. It looks better, right? Actually, there is almost no difference between the two. This is not a good example. Instead of using the animated cylinder for demonstration, let's just use the final scene. Since the flamethrower is a fast-moving fire, here you can see in the rendering, the grid-based motion blur on the right looks better than the ray-traced motion blur on the left. Great! We have completed the fire dynamics and shading. Now let's add some embers to the fire using Phoenix particle emission feature. In the source, we will set the particle type to drag and use a particle shader to render them out. One of the benefits of using the drag particle type is that they follow the motion of the fluid simulation, which looks more realistic than simply emitting and shooting out particles without considering the fluid dynamics. This is the particle shader I used for the embers. I gave it a yellowish color to match the appearance of real embers. Currently, Phoenix does not support self-illumination in the particle shader, so I used a high value of the diffuse multiplier to give the embers a bright appearance. I also added size variation in the particle shader for the particles, making the embers look less uniform and more realistic. To add a final touch of realism, we can apply color correction and add lens effects in the V-ray frame buffer. All right, there's still one thing left to consider: the smoke shading. The ray-traced option delivers a more believable and accurate representation of light scattering, especially in areas of heavy smoke density. Please note that this option may lead to longer rendering time. Here you can see the option to switch to ray-trace scattering. Basically, the approximate scattering would never refract the ray as it goes through the smoke, so it would produce God rays, while the ray trace scattering would allow the ray to change directions inside the smoke. Here is another frame of the rendered image. As you can see, the ray trace scattering looks more believable than the default approximate plus shadow option. In addition to the sources for the flamethrower and the burning wood, we also create a source for the explosion in the scene. There are a few settings worth noting for this source. First, we set the emit mode to volume inject and animated the inject power from a value of 5.0 at frame 0 to zero point 0 at frame 20. This helped to create a decay of the explosion over time. The time-base particle age mode in the Phoenix source allows you to set keyframes for the inject power without having to worry about matching the timing of the explosion exactly. It means that for each fluid emission from the particle would be animated independently based on the curve, starting from their birth. This way, if the particles are born at different times, each of them would live through the animation individually. This is a very handy option for creating procedural pyro effects. Finally, we have reached the last stage of the process. To improve rendering performance, I made two changes in V-Ray. I adjusted the max subdivisions of the image sampler and the probabilistic volumetrics. By lowering these values, I reduced rendering time while still maintaining acceptable image quality. The default value for the direct sample is set to 20. You can experiment by lowering this value to 15, 5, 3, or even 1 to find the optimal value. Note that this value may vary across different scenes. In conclusion to this video, I demonstrated how to create convincing pyro effects using Phoenix and thinkingParticles. I built the model as if I was constructing it in the real world, making sure the geometry was a watertight model with clean UVW mapping and aligned the local z-axis for the wood planks. For the rigid body simulation and destruction, we used thinkingParticles. When generating particles for the Phoenix source, make sure they form clustered formations. To achieve a realistic fire, try masking the source with an animated map. Pay attention to the conservation method you choose. Avoid overlapping fire and smoke by generating smoke from burning fuel. Add forces to make the results look more natural and realistic. Modulate the fire opacity with V-Ray distance. Use grid-based motion blur for fast-moving fires, such as flamethrowers. To add flying embers, enable drag particle emission in the Phoenix source and render them with a particle shader. Lastly, the time-based particle age option is very handy for procedural pyro effects. To improve rendering speed, we tweak the max subdivs and probabilistic volumetrics. We also added a final touch by applying color correction and enabling lens effects in the VFB. Thanks for tuning in, and I'll see you for the next part.